let's get going. So we were discussing various notions of symmetry, right? And in particular, we learned what it means to be symmetrical with respect to a circle. So okay. And we agreed that if Z and Z star are symmetric with respect to the circle, then that was saying that Z is equal to squared of 1 over Z minus A complex conjugate plus A, right? Because this is A and this is Z, then as we go out along this ray, like this, okay, the closer we are to A, the more we're sent out along this ray. So this thing, oops, change color. C star should be given by this expression, because in coordinates, so in xy coordinates, what would this be? This would be saying that x star or y star is equal to squared of x y minus minus a over x minus, oops, there's no brackets around a, plus a, because when we write this expression in complex notation, this is the same as z minus a times z minus a complex conjugate, and this thing cancels, so it gives us this expression like this, right? Everybody feeling okay with that? Yeah? All right, so the theorem we're going to prove today and then later use is the following. So, theorem. Given a circle or line which we're going to denote by C, if Z1, Z2, Z3 are pairwise disjoint points on C, then Z and Z star are symmetric with respect to C, if and only if Z1, Z2, Z3 complex conjugate is equal to this thing. So this is the statement I put up on Tuesday, and now we're going to prove it. Okay, so let's try and save space. So proof. Let's first take the case when C is a circle. So, okay, so the the key thing we're going to use to prove this is the fact that we learned that this cross ratio stuff is invariant when we take Mobius transforms, i.e., so recall if T is a Mobius, then we found out that T of Z, T of Z1, was the same as this thing. Oops. That's what we learned, right? That's a theorem from last time. So that allows us to do these kind of transformations of this cross product expression. Another thing to notice is that the cross product, let me just write out the definition just one time. The cross product which is given by this thing, has this nice property that if we take complex conjugates through this, then this is taking the complex conjugate of this thing, and that's the same as that thing breaks down into taking the complex conjugate of each part of this expression, right? Because this is what complex conjugates do. If we have A plus B, or A times B, more interesting. Well, maybe let's just do Z times W. Times W, complex conjugate is Z times W bar, right? So that when we put this thing through this, then we'll put the bar on every part of this stuff, on every expression inside this, because that's what complex conjugates allow us to do by this thing. Yeah. So this is the same as Z bar, this thing bar, this thing bar, this thing bar, like this. Yeah. And we're going to use that shortly in the proof. Okay. So I'm going to erase the board, and we're going to get to work on this. We have point Z, Z1, Z2, Z3, and we're going to take the complex conjugate. And the first thing we're going to do is we're going to act with this Mobius transform that simply subtracts A from everything. Okay? Because that's a Mobius transform as well, right? So Mobius transforms T of Z is equal to, oops. So this is a different A. This is just the general form. Let me put it, okay, let me do capital A, Z plus B over CZ plus D, right? So that includes the map that just takes Z and adds a constant B to it. So we can set A to be 1, C to be 0, D to be 1, and then we're going to have Z plus B is an example of such a map, right? Cool. So this thing is equal to Z minus A, Z1 minus A, Z2 minus A, and Z3 minus A, like this. Yeah. What do we do then? Oops, I forgot to put a bar on top. Then we're going to put the complex conjugate inside this expression. I don't want to rewrite everything, so let me just put a bar here, a bar here, a bar here, and a bar here. Get rid of this. Like this. And then what we know that these guys are all on the circle, right? So we know that Zi minus A squared is equal to R squared, but that's the same as saying that Zi minus A bar, Zi minus A is equal to R squared, right? So that's the same as having Zi minus a bar is equal to r squared over a, like this. So we can replace each one of these guys with that thing. Let's put it over here. And then we're going to have r squared. Oops, Z1 minus a. Like this. Yeah? Now, let's take the Mobius transform that does this, and let us do this. Let's do this. Let's do like this. Because no, let's do it like this. Because when we put these guys into this, then we are just going to get Z1 minus A. And all of these guys will be nice and simple, and this thing will be turned into something else. But first, just agree with me that this thing is just a Mobius transform again, because for the right choice of coefficients, we get something like this. Yeah? So we have the right to just apply the Mobius transform to everything inside this expression, and it doesn't change the cross product. Yeah? So let's do that. So the first term, applying this to this thing, we're going to get r squared over z minus a complex conjugate, and then all of these guys gets turned into something rather nice like this. Z1 minus a, Z2 minus a, Z3 minus a, like this. Yeah? Cool. And then finally we do the Mobius transform, which is just adding a to everything. Yeah? Which is T of z equals z plus a. Again, it's a Mobius transform, we can apply it to everything, and then we get this. We get, I'll put it here. Complex conjugate plus a. And then here we have z1, z2, z3. Yeah? So that is this thing is equal to this thing, and our claim that we have z and z star being symmetrical is exactly saying that this is equal to z star, z1, z2, z3, right? Yeah. But what are we looking at here? So if you just fixed your z1, z2, z3, and then think of the mapping z goes to, this itself is a Mobius transform, as we discussed, right? It's a Mobius transform, and it's an invertible one. It's one of the non-trivial ones, which is invertible. So what we're looking at is that the Mobius transform given by this applied to z star agrees with the Mobius transform given by the same agrees with the Mobius transform. Start again. What we're looking at is that the Mobius transform defined by this applied to z star agrees with the same Mobius transform applied to this thing. Yeah, but they are bijections. They are bijections. So the only way that's possible is if this thing is equal to this thing. Yeah? Give me a thumbs up if that makes sense to you. Okay, cool. So this implies that r squared z minus this thing plus a is equal to this. Yeah? So that's exactly what we claimed. Yeah? So defining symmetry via so defining symmetry via the claim that z1, z2, z3 complex conjugate is equal to is indeed giving us exactly the notion of symmetry we expect. Huh? Okay, cool. Now we're going to do this for a line. So given a line, L, let us make a smart choice of points Z1, Z2, Z3 on the line. So recall the formula again for the cross product is this thing. So if we choose Z3 to be infinity, that is still a point on the line. So let Z3 equals infinity. But then this expression here when you put infinity into this, we see that that this guy is going to cancel with this guy, and all we're going to get left with is just z minus z1 over z2 minus z1. So this thing is the complex conjugate of z minus z1 over the complex conjugate of z2 minus z1. Like this. Because again, when we put this z3 equals infinity, then this is just this thing just becomes, let me rewrite this. This thing just becomes 1. So we can rewrite this as z minus z1 over z2 minus z1, and then z2 minus z3 over z minus z3. So if we look at this thing here, as we let z3 go to infinity, this thing is just tending to 1 no matter what our choice of z actually is. Yeah. So at infinity, this expression here is exactly 1. Yeah. So we just end up with this expression right here. Yeah. And the statement that z and z star are symmetric across the line is the statement that this is true. And again, we're going to make the choice of z3 being infinity, which again reduces down to this, so z star minus z1 over z2 minus z1. Yeah? So what is the consequences of that? Let me create some space. Well, if we take the absolute value of both sides of this, then what we see, we have the absolute value of z1 minus z bar over the absolute value of z2 minus z1 bar, and that's the same as the absolute value of z star minus z1 over z2 minus z1. And taking the complex conjugate doesn't change the absolute value of any complex number, right? So this thing is, oops, this is 1 here. This is 1 here. So this thing is the same as this thing. So, and let's stop writing the complex conjugate at the top here, because again, it doesn't change anything when you take the absolute value. So it's z1 minus z is equal to z star minus z1. And that's for any z1 on the line, right? Right, so what does that mean? So this is the line L, this is z, This is z star. And for any line L, sorry, for any point z1 on the line, then this distance is the same as this distance, which is the same as saying that z and z star are symmetric across the line. Yeah? Cool. So this is how we can have this generalized notion of symmetry theorem. If C is a line or circle, and thing here. So if C is a line or circle, and Z star are symmetric with respect to C, then, and T is a Mobius transform, then T of Z and T of Z star are symmetric with respect to T of C. So, exercise. Given this Mobius transform, we are going to work out the image of various things using this guy. So the first thing we're going to work out, I believe, is a circle centered on 1 of radius 1. So find f of like this. Okay, so solution. How are we going to do this? So let's draw the complex plane over here, and let's draw the thing we're actually going to consider the image of, like this. Okay, and we have a couple of things to, well, we have several things to help us figure out these images. The first thing is that this thing preserves angles. So that helps us tell what is happening when we have things which are crossing, then the angle has to be preserved. That's the first thing to notice, okay? And the second thing is the symmetry properties. So we can also put in specific values into our thing, into our Mobius map, to help us figure this stuff out. But before we do that, looking at this circle, what do you think it's going to be? Is it going to be a line or a circle when we map it? We have two possibilities. Is it going to be a line or a circle? What do you think? Let's look at this thing. So what point is being sent to infinity by this Mobius transformation? Negative I, right? Yeah. So unless we hit negative I, we are not actually going to be sent to infinity. So most likely this thing will actually be well, not most likely, for sure it's going to be actually a circle. Yeah? It's going to be a circle. Cool. All right, so what we can do, we can start to put in some points and then start to use some symmetry properties. Okay, so what points shall we put in? So 0 is a convenient point to put in. So f of 0 is equal to -1, right? 2 is a convenient point to put in. Yeah. So let's put in f of 2. So we put 2 into this expression, we're going to have 2 minus I over 2 plus I. That's multiplied by its complex conjugate. So that's the same as 2 minus I squared over 5, right? Multiplying complex conjugate here. And what's that? That's going to be 4. And then I squared is minus 1. So it's going to be 4 minus 1, which is 3. And then multiplying this, we're going to have this. We have 2 times I carrying twice. It's minus 4I over 5, like this. This is this point. Yeah. So let's start to draw some of the stuff. And what do we have? We have that 0 is mapped to minus 1 over here. And we have that 2 is mapped to this thing, which is, say, somewhere over here. So this is f of 2. Maybe I put this as f of 0. Cool. What about this thing acting on the real line? This is a guy we looked at before. So if we look at this thing acting on the real line, this was the guy that sent the upper half space into a circle. And looking at this on the real line, it sends the real line just to the unit ball, which isn't that useful to us. Don't think it's that useful to us. Okay, let's look at what it does in terms of symmetry. So this thing, if we consider f of 1, right? So on this circle, 1 is symmetrical to infinity, right? Because 1's the center of the circle. Yeah. So 1 and infinity are symmetrical with respect to this circle. So the image of the circle, which is what we're trying to find, will have to be such that f of 1 will have to be symmetric to f of infinity. Yeah. So f of 1 is 1 minus I over 1 plus I, right? And that's the same as 1 minus I squared over 2, which is the same as 1 minus I. So 1, so times I, so minus 1, oops. And then minus 2I over 2, so that's minus I. Yeah? So f of 1 is minus I, which is here. And f of infinity is what? That is just minus 1, like this. So this is minus I, and then this is minus 1. Oops, minus 1. Wait, we have a mistake. So f of 0, yeah, this is not minus 1, it's 1. This is just 1, right? So this here is 1. Okay, so it's going to be a circle, and these points are going to be symmetrical with respect to the circle. Yeah. So if it's symmetrical with respect to the circle, that means that the circle is going to have to cross this perpendicularly. So the center of the circle is going to have to be somewhere on this line here. So yeah, look, if we have points which are symmetric with respect to a circle, right? Then the direction which goes from this point to its symmetric point has to cut perpendicularly through the circle, and indeed the center of the circle has to be on the same line as these points. Yeah? Yeah. So f of infinity is 1 right here. And the direction that goes from -1 to 1 is this direction given by 1 plus I. So we know that this, if we let A be the center of the circle, then we know that A plus IB plus lambda times 1 plus I, this is producing this line, right? And this thing has to go through these points like this, yeah? And wherever the center is, we can use this to reduce this down to just one coordinate. Yeah, because for some lambda, this thing has to equal 1. So this is 1 for some lambda. Along with the real numbers, right? Because this thing here is one of the guys we have to go through with this line. So that's true. So that gives us a way to write this A plus IB equals 1 minus lambda 1 plus IB, which gives us one coordinate instead of 2. Okay, so this is what we're going to use, and we're going to use the fact that we have these guys going through our circle. So these guys are on our circle. So this is on our circle, and this is on our circle, right? And then we're just going to calculate these radii. So 0 is minus 1, okay. It's minus 1. All right, so we have to have that A plus IB minus 1, which is plus 1, squared, that's going to be the radius of the circle, is going to be the same as when we do A plus IB minus this guy, which has got coordinates like this, 3 minus 4I over 5, like this, right? So then we can put in our lambda. So then we're going to have this thing here. We're going to have 2 minus lambda. What is this? This is not, there's no B here. Like this, squared. And then this is 1 minus lambda 1. Like this. And then minus this stuff here. Over 5. Okay, so this has to be true, right? Because they're on the circle, right? And the center of the circle we can represent like this. So this gives us something which is an equation just in 1 lambda, right? Gives an equation just in 1 lambda. Yeah? And then we are able to solve this. We are able to solve this lambda. And I want to make sure I do not make errors, because this was really bad when I made errors previously in working them out. Okay, let's do this. So when we have 2 minus lambda squared, taking the real part of this thing, and then plus lambda squared, which is this thing, right? And then that thing has to be equal to, let's take the real part of this. So then we have, we're going to have 2 over 5 minus lambda squared like this, right? Because that's 5 over 5, and we're taking 1 lambda away. And then for the imaginary part, we are going to have 4 over 5 and then minus lambda, right? Squared, let's check. Yep, that looks good. And let us expand this out. And then what do we get? We're going to get 4 minus 4 lambda plus lambda squared. And expanding this thing out, we are going to get 4 over 25 plus lambda squared minus 4 lambda over 5 plus 16 over 25 minus 8 lambda over 5 plus lambda squared. And then we can, we actually have a 2 lambda squared here because we get a lambda squared from here. So we have these 2 lambda squareds will cancel like this, this, this. And then what does that give us? That gives us lots of things. So let's put this stuff all together. So let's multiply this. This is a mess expression. Okay, so the 16 plus 4 now becomes 20, so it becomes 20 over 25. So then 20 over 25 is 4 over 5, right? Write that better. So we have 4 over 5 from adding these things together. And then from this thing, we're going to have minus 12 lambda over 5. And what we have from this side, we have this thing. So let's write this as 20 over 5. So let's put this thing over here. So let's write this as 20. What's it over 5? So 5. This is it correct? Yes. 20 over 5 minus 4 lambda. Let's put this over 5. So 20 lambda over 5. So this is equal to this. Let's put that on the other side. So put this on the, let's add this thing to that side. So then that implies that we have 8 lambda over 5. And then putting the other stuff on the other side is equal to 16 over 5, which implies that lambda is equal to 2. Good. Cool. So, since we know the center is on a line like this, which has to go down from, or up, whatever you want, from 1, we've now found that this lambda has equal to 2. So our center, therefore, has to be given by this thing right here, right? So from star, this implies that our center, A plus IP, has to equal this thing. So it's 1 minus 2, which is minus 1, and minus 2i. Okay, and this being the case, we can now find the radius because we can put into either of these things. So this is the radius squared. So if we put into this thing, then we have that we're just going to have that minus 2i, because we're just adding 1, squared is the radius squared, which implies that the radius is equal to 2. Okay, so it seems that we are with a circle of radius 2 centered on 1 minus 1 minus 2. Okay, so minus 1 minus 2 is something like this. Minus 1 minus 2 is like this. So if it's got radius 2, then it should go through. Should go through like this. Right, okay. So it goes through like this. And this point is this point over here, which, you know, it's just approximation, actually must live somewhere here. What was this? This was f of 2. Okay, so this is what our circle must be, and sure enough, it lives on this line, and this point are symmetrical with respect to the circle. Okay, all right, pretty hesitant performance there from me. So I was doing these calculations for a long time. It's very, very easy to go in the wrong direction, get something completely nonsensical. What is kind of good about this is that if you do, then the thing doesn't fit together. So there's so many relations that these things have to satisfy that if you make a mistake, then it just doesn't fit together. What's kind of amazing is that these mappings exist at all, because yeah, there are so many different relations they have to satisfy. F of z again is this guy, z minus I over z plus I, and then it's find image of the set of I plus t, where t is real. And I'm just going to write that as I plus the real numbers, like this. Okay. Is this a line or a circle? What do you think? Is it a line or a circle? Yeah. Right, it doesn't go through the thing that's sent to infinity, so it has to be a circle. Yeah? Cool. So we're going to try and use stuff that we know. Okay, so we see that this line is perpendicular to this imaginary line right here, right? So if we look at what the mapping's doing to the imaginary line, so we do f of, say, alpha times I, then what is it? Well, actually, you can just make things easier, right? Let's just pick some points on the imaginary line. So if we just take in f of 0, then what's that? That's equal to just minus 1, as we saw before. If we do f of infinity, that's equal to 1. And if we do f of I, then that's equal to 0. Yeah, and these are all things on the real line. These are all points on the real line. Yeah, so that means that the image of the imaginary line is the real line. Yeah, because it's a line or a circle, it's obviously going to be a line because it goes through minus I, and the line it is the line that goes through these 3 points, and there's only one, and that's the real line. Yeah, like 2 points would be enough. So f of the imaginary line is this real line. Yeah? Cool. What else do we know? We see that our horizontal line is cutting perpendicularly through the imaginary line. So in the image, it's a circle that has to do the same thing. So this thing has to cut through perpendicularly to this line here. Yeah? Yeah? So if we zoom in right here and see where this point is mapped to, wherever it is, say it's mapped to here, if we look, then it has to cross perpendicularly. Yeah? Cool. So if it crosses perpendicularly, what do you expect about the circle? What information does that give you about the circle? The center has to be on the real line, right? Otherwise there'd be an angle, right? So since it crosses perpendicularly, I can't really draw it well. No? The center has to be on the real line. So f of I plus r is a circle with center on the real line. Cool. So that makes life simpler for us because it's easy to calculate things, and we can just then plug in values into this thing and see where they go, and use that to determine what the center could possibly be. So what convenient values can we put into this? Well, the first convenient value is just I itself, right? And that sends us to 0, right? So 0 has to be point of the circle. In fact, 0 is this point where we, is that correct? Yeah, 0 is this point where we cross like this. 0 is this point right here, yeah? Okay, and what else? What are the cool thing? What are the easy values? Let me do the ones I did before. Let's do f of 1 plus I. And if we put that in, then we're just going to get 1 over 1 plus 2i like this. And then let's clean that up. So that's the same as 1 minus 2i over 5 itself. Yeah, just doing our complex conjugate stuff. So then we have that letting C be the center of the circle, we have that the distance of C to 0 is just C squared, right? So that's right, it's just C squared. It's going to be the same as the distance of the center away from this point, which is 1 minus 2i over 5 minus C squared. And then this we can do some algebra with. So then this is 1 over 5 minus C, everything squared. And then this thing is just 2 over 5 squared, like this. And what we're looking at is a nice quadratic equation in terms of C, right? So then we're going to have C squared. We are going to have minus 2C over 5, and then plus 1 over 25. And then this thing is going to be 4 over 25, right? And then the C's cancel, the C squared cancel. So then that's going to give us 2C over 5, putting this guy on the other side, is equal to 5 over 25, which is 1 over 5, which implies that C is equal to 1 over 2, like this. No? So the center of the circle is at 1 over 2, so it's here. And the circle is actually curling the other way. Like this, and its radius is also a half. Okay. Cool. Let's... Yeah. I mean, that's it. That's the only thing it can be. Yeah. So that one wasn't too bad. Let's do another one. So part C. Find the image of the circle of radius 2 around 0. All right. Circle of radius 2 around 0. Is it going to be a line or a circle? Come on. Line or circle? It's a circle again, right? It doesn't go through I, right? It's got to be a circle. Let's draw it. There's this. Okay, it has again the convenient property of cutting through the imaginary axis exactly perpendicular. Yeah. So the image again. So this point here. So this is 2i, and this is minus 2i. So these guys are on the real line, and they are going to whichever way they are around. If this guy is here and this guy is here, I don't know, but they're going to cross the real line at 45 degrees, just like this guy here. No? So that means that what? What's the consequences of that? Yeah, then halfway in between them is the center, and the center's in the real line too. Yeah, so this is a circle, and it's centered on the real line. And it's exactly halfway between these 2 points, so we can just find what these 2 points are. So f of 2i is I over 3i, right, which is 1 over 3. And f of minus 2i is minus 3i over minus I, right, which is just equal to 3. Right, so we are here at a third, and here we are at 3. Get rid of some extra detail. And indeed, halfway between them is the actual center. So 3 minus the third, that's the same as 9 over 3 minus the third, which is 8 over 3, right? So that's the diameter. So the radius is 4 over 3. So then the center is a third plus this thing, so it's going to be 5 over 3. So the image of this thing, so f of c is the boundary of the ball of radius 4 over 3 around 5 over 3, like this. Yeah? Cool. And just to make a little check that all the things we've been talking about actually work, let's look at symmetry. So let's look at 0 and infinity, which is symmetrical with respect to this thing. And then f of 0 is -1, right? And f of infinity is 1. So f, we are centered here at 5/3, right? This is where we are, right here. And f of infinity is like somewhere here, right? So this is f of infinity here at 1. And f of f of 0 is at -1. So if this here is 0, then -1 would be over here, right? And so this is f of 0. So these things do indeed look like they are symmetric, right? At least on the right line, right? And if this is correct, then we can actually check that the distances are doing what we expect, right? So what is this distance here? So again, f of infinity is 1. So this distance here is what? It's just 2/3, this distance, right? And the radius of the circle is 4/3, right? So in principle, we should have that if we take this distance, so if we take 1/2/3, okay, and then we multiply it by the radius squared, which is 4/3, yeah, and we add it to the number 5/3, which is the center, but we're going in this direction, so it's a negative thing. So we take this quantity minus plus 5/3, right? So if everything is correct, then this thing should be exactly -1, right? Yeah, because that's symmetry across a circle. Yeah. So let's check if that works out. So then what is this? So then this is -3/2, and this is 16/9 plus 5/3, and so we're going to get -8/3 plus 5/3, which is indeed -1, right? So this symmetry is exactly happening as claimed. Yeah. Cool. So these are the right things. All right. So I'm gonna give you some past prelim type questions where it's exactly that kind of thing. You're given some explicit Mobius transform, and you're asked, what is the image of this? What's the image of that? The tools, again, are angles are being preserved and symmetries are being preserved. Yeah? And with those pieces of information, you can piece together what you know and find the function. And it can be quite intricate sometimes, but there is an answer, and you will ultimately find it. So, and it's worth practicing this, because this is the kind of question that gets asked quite regularly. If you look back on past prelims, you see there's lots of these type of questions. When we meet next Tuesday, I will give you the proof of this theorem that I didn't prove today, and it is quite short and neat. I just blanked on it, but it's not hard to prove given what we've learned today. All right, so that's it for today. Have a great day, and I will see you all next week. Bye-bye.